Meet HD 140283, or as we like to call it, the Methuselah star. This celestial body has a reputation that precedes it being known as the oldest star we've had the pleasure to observe. Now, you might be wondering, how old is old? Well, we're talking about an estimated age of approximately 14.5 billion years. That's right, billion with a B. Now here's the kicker. According to our best estimates, the universe itself is around 13.8 billion years old. So how could a star possibly be older than the universe itself? The answer lies in the margin of error in age estimation. When we talk about the age of celestial bodies, we're dealing with such mind-bogglingly large numbers that a small margin of error can equate to hundreds of millions of years. So, while it's possible that Methuselah might be older than the universe, it's also plausible that we've overestimated its age by a bit. But how do we even begin to calculate the age of a star, especially one as old as Methuselah? It's a fascinating process that involves studying the star's chemical composition and its distance from Earth. Methuselah, for instance, is composed almost entirely of hydrogen and helium, with very little presence of other elements. This suggests that it was formed before these elements were widely available in the universe. Additionally, by measuring the star's parallax, we can calculate its distance from Earth. Once we have that, we can determine its intrinsic brightness or luminosity. By comparing this with the star's apparent brightness from Earth, we can estimate its age. So there you have it, a star that might be older than the universe itself, or might just be a very, very, very old star. Either way, it's a remarkable testament to the longevity of celestial bodies. The Methuselah star holds the record for the oldest known star, but what about galaxies? Galaxy GNZ 11 takes the cake for being the oldest and most distant known galaxy in the observable universe. This ancient celestial wonder was first discovered through the Hubble Space Telescope, its light having journeyed across the cosmos for an astounding 13.4 billion years before finally reaching us. To put that into perspective, our universe is only about 13.8 billion years old. So when we're observing GNZ 11, we're essentially peering back in time to an era when the universe was a mere 400 million years young. Now you may be wondering, how do we know this? How can we possibly calculate the age of something so incredibly distant? The answer lies in the science of redshift. As light from distant galaxies travels towards us, it's stretched by the expansion of the universe. This stretching shifts the light towards the red end of the spectrum. By measuring this redshift, we can calculate just how long the light has been traveling to reach us. But what about the galaxy itself? Well, GNZ 11 is quite a marvel. Despite its age, this galaxy is not some puny, shriveled-up relic. It's a bustling cosmic metropolis, roughly 3 billion solar masses in size. What's even more interesting is how quickly GNZ 11 is forming new stars. It's churning out new stellar bodies at a rate 20 times greater than galaxies today. This high rate of star formation is a testament to the rich reserves of gas and dust in the early universe, providing ample material for the birth of new stars. From individual stars to entire galaxies, we've traveled back in time, but can we go even further? Let's continue our journey through the cosmos and find out. Cosmic microwave background radiation, or CMB, is like a baby picture of our universe. This metaphor, while whimsical, is not far from the truth. The CMB is a snapshot of our universe taken when it was a mere 380,000 years young, a blink of an eye in cosmological terms. So how did we come across this cosmic baby picture? Well, it was discovered quite serendipitously by Arno Penzias and Robert Wilson in 1965. Initially, they thought the faint microwave signal they detected was due to pigeon droppings on their antenna, but after cleaning up and still finding the signal, they realized they'd stumbled upon something far more significant. Their discovery, which earned them the Nobel Prize in Physics in 1978, provided the first strong evidence for the Big Bang theory. The CMB is essentially the afterglow of the Big Bang, a faint echo of the universe's explosive birth. It's a cosmic background noise that pervades the entire universe, stretching across the cosmos like an ethereal shroud. It's uniform in all directions, save for minor fluctuations, which are crucial as they're the seeds of galaxy formation. Now, why is the CMB so significant? It's because it provides a glimpse into the universe's infancy, a time when it was a hot, dense plasma. As the universe expanded and cooled, protons and the electrons combined to form neutral hydrogen, allowing light to travel freely for the first time. This light, the CMB we observe today, provides a snapshot of the universe at that pivotal moment. This cosmic radiation, the oldest object we can observe, helps us understand the fundamental properties of our universe, its age, shape, and composition. It's an invaluable tool in cosmology, a testament to our ingenuity in deciphering the cosmos. From the oldest star to the oldest galaxy, and finally to the oldest observable evidence of our universe, we've journeyed through cosmic time. The universe, it seems, is full of ancient wonders.